In this video, we're going to start subsection 6.5.2 about using row reduction to calculate the determinant. In chapter 3, we'd seen that we can use row operations to transform a matrix into a nicer and more useful form. And we've actually just seen in the previous subsection that row operations can affect the determinant. If we put these two ideas together, we can use row operations to put a matrix into a form whose determinant is easier to calculate. But we must carefully keep track of the effect of each operation so that we can work out the determinant of the original matrix. To this end, we're going to look at a notation that mixes row reduction and properties of theorem 6.5.1 that we saw in the previous video. And that is Determinant-Row-Operation-Notation. So while row reducing to evaluate a determinant, we can use theorem 6.5.1 to create an equation of determinants while writing the row operation above the equal sign. For example, this operation here, if we want to write an equation of determinants, well, we'll write the vertical bars of the determinant, so 3, 5, 2, 4. We'll write equal sign, and then we'll write the vertical bars of the next determinant. And if we remember from theorem 6.5.1, this equality is not right. This equality is not right. First of all, I should write the row operation above the equal sign. When we do a row interchange, the determinant becomes negative. So if we do this evaluation real quick on this side, the left-hand side, we get 3 times 4 is 12, minus minus is plus 10, that determinant is 22. Over here I have minus 10 minus 12, or minus 22. So if I want to create an equality of these determinants, I have to fix one side or the other. And since we work from left to right, I'm going to fix the right-hand side to keep track of all the changes. And to fix that, I need a negative, right? 22 is negative 22, which means that the original equation can be fixed if I put a negative sign outside that determinant. And so this is this row operation translated into determinant-row-operation notation, the row operation above the equal sign, determinant bars instead of the square brackets, and the equation made true by fixing it, in other words, by taking account of the effect of that row operation on the determinant. Next kind of row operation, if we add two rows together, well, that becomes, so 3 minus 5, 2, 4, equals with the row operation on top, and then 5 minus 1, 2, 4 is when we've added those two rows together. On the left, if we evaluate that determinant, we get still the same 22. On the right, what do we have? 20 minus minus plus 2, 22 as well. Those are equal. And so in fact, there is no fix. There's nothing that I have to add in front here to make this a true equation. And we remember from this theorem 6.5.1 that indeed that adding a multiple of one row to another did not change that determinant. So I can simply change the brackets into vertical bars, change the arrow into an equal sign, put the row operation there, and I have a true equality between those two determinants. Last operation, if we multiply a row by a constant k, we'd seen that that affects the determinant as well. And so let's translate that into the new notation. So 3 minus 5, 2, 4 as a determinant equals row operation above 1/2, row 2, and then 3 minus 5, 1, 2, when that second row has been multiplied by 1/2. If we take the determinant on both sides, well, the left hasn't changed, so we're still getting 22. Here we're getting 6 plus 5, which is 11. And so if we want to fix this to make a true equation, we better multiply this side by 2, right? And so that is the fix that is necessary to make this a true equation of determinants. Now I want us to notice something, a couple things actually. First of all, when we multiplied this by 1/2, the property from theorem 6.5.1 says that the determinant of the matrix that results gets multiplied by 1/2, right? So 22 times 1/2 is 11. That's true. Right? But if we go in this direction, if we want to sort of repair the damage to make this an equal sign, this has been multiplied, 22 has been multiplied by 1/2. To restore the equality, I've got to multiply by 2. Another thing to notice, this 2, that's the reciprocal of 1/2, right? 1 over 1/2 is 2, or 1 over 2 is 1/2. Those are reciprocals of another. And then one more thing to notice is it kind of looks like this 2, right? We have 2, 4. It kind of looks like that's just been factored out. That's not at all what's happening, but that's just a handy memory aid, and that in fact is this takeaway. In determinant row operation, multiplying a row by k, here our k is 1/2, by multiplying a row by 1 over k, so our 1 over k is 2, then that looks like factoring out k from the determinant, right? So if you multiply by 1 over k, it looks like factoring out k from the determinant. So we're going to use this notation in subsequent videos to do row operations, multiple steps, keep track of the operations. In other words, we're going to fix the equalities by adding either a negative or a k multiple when we need to reduce a matrix into an easier form and calculate the determinant. See you in a little bit for that process.